Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Hello, everyone. It's my great pleasure to invite Professor Li-Song Xu and his student Miao Wang to come to Microsoft and give a talk on bandwidth allocation in TCP friendliness and peer-to-peer streaming. Professor Xu got his PhD degree from North Carolina State University in year 2002 and was a postdoc research fellow from 2002 to 2004. From 2004, he became assistant professor in University of Nebraska-Lincoln in the CS department. He is a recipient of NSF Career Award in year 2007 and the University of Nebraska Outstanding Teacher Award for 3 consecutive years in a row, 2006, 2007, and 2008. He has a number of outstanding works, including the optical burst switching and big TCP and cubic TCP, which, to my understanding, is currently the default TCP protocol used in Linux systems. He's currently working on 2 projects, exploring the design space of TCP-friendly traffic control protocol and peer-to-peer streaming systems. In this talk, Professor Xu and his student is going to talk about the recent progress of their work. Without further ado, let's hear what Professor Xu has to say.
Okay, thanks for the introduction. Today I'm very happy to talk about our work on this bandwidth allocation problem in TCP friendliness and peer-to-peer streaming. Okay, so this is joint work with my student Miao Wang, Jie Feng, and also Professor Bai Ramamurthy at the University of Nebraska-Lincoln. Okay, so this talk consists of 2 parts. First, TCP friendliness, and the second part, peer-to-peer streaming. The first part, TCP friendliness, mainly considers the bandwidth allocation problem in the Internet backbone. While the second part, P2P streaming, mainly considers the bandwidth allocation problem at the edges of the Internet, that is, the upload capacity of users. So I'll talk about the first part, and my student Miao, okay, so right over here, and he'll talk about the second part, P2P streaming, because he did all the work on this P2P streaming, and also he'll give a similar talk this Friday at P2P 2009. Okay, so let's start with the first part, this TCP friendliness. Okay, so the Internet. So 10 years ago, the Internet was a homogeneous Internet because at that time, most Internet traffic was TCP traffic. In addition, all those TCP traffic was controlled by exactly the same traffic control algorithm, the AIMD algorithm. But now we have a heterogeneous Internet because there are more and more UDP traffic, mainly because of those multimedia streaming applications and also peer-to-peer applications. And also there are more and more traffic control algorithms for not only controlling TCP traffic, but also for controlling UDP traffic. So for example, for TCP, in addition to this AMD, we also have the TCP cubic, the algorithm that we developed 5 years ago, and now is the default one of Linux. And also there is the TCP compound. So this is the default algorithm of Windows Vista. I'm not sure whether this is also the default one of Windows 7. Okay, yeah. And there is the TCP fast. The TCP fast was developed by Professor Stephen Low at the California Institute of Technology. And also is being commercialized by his startup, the FastSoft company. Now for UDP, we have this TFRC, stand for TCP-friendly rate control, and this is an Internet standard. And also we have this UDP LED BAT, stand for the low extra delay background transport protocol, and this is the one used by BitTorrent for controlling UDP traffic. Okay, so now we can see that we have such a heterogeneous Internet with so many different traffic control algorithms. So for such a heterogeneous Internet, there are 2 important problems. First, the fairness problem. So that is how to make sure that different traffic control algorithms, they can fairly share the internet. So this is a very hard problem, and this is also a very active research area. The second problem is this friendliness problem. So this is a related but different problem. And here we consider how to design a new traffic control algorithm so that it's friendly to existing algorithms in the internet. In other words, here we consider how to design a new algorithm so that it's safe to deploy it in the internet. And our work focuses on the second one, this friendliness problem. Okay, because there are so many different traffic control algorithms, so there are several different types of friendliness problem. The first one is how to design a new TCP traffic control algorithm such as TCP big, TCP compound, TCP fast, so that it's friendly to the existing TCP-AMD algorithm. And second, how to design a new UDP traffic control algorithm so that it's friendly to the TCP-AMD. And also, if in the future this TCP compound replaces this TCP-AMD and becomes the most popular one in the internet, and then we should also consider how to design a UDP traffic control algorithm so that it's friendly to TCP compound. So we have studied all those friendliness problems, and in this talk, I'll focus on the second one, the one with the most concern. That is how to design a UDP traffic control algorithm so that it's friendly to TCP-AMD.
Can you explain again the difference between fairness and friendliness?
Okay. So for the fairness problem, actually, we are interested in the impact of both. For example, now let's say if we have two algorithms, algorithm A and B. When we consider the fairness problem, we consider the impact of A on B and also the impact of B on A. So the impact of each other. But for the fairness problem, we consider only the impact of algorithm A on algorithm B. Okay, so only one direction. So this is a related but different one. So maybe this one is easier than the first one. Okay. So that's why, for example, here we consider the second one, how to design a new UDP traffic control algorithm so that it's friendly to the TCP-AMD. So we consider the impact of those UDP algorithm on this TCP-AMD algorithm. Now, so in this talk, we consider the TCP friendliness problem of UDP traffic, or in other words, how to control the UDP traffic so that it is friendly to TCP-AMD. Now, note that even though in this talk we consider only TCP-AMD algorithm, but our work can be easily extended for controlling UDP traffic to so that it's friendly to other type of TCP traffic, for example, TCP big or TCP compound. Now, so this problem was first studied in late 1990s because of the concern that UDP alone without congestion control could lead to TCP starvation or congestion collapse. So in the late 1990s, this deterministic TCP friendliness was proposed as a fundamental design guideline for controlling UDP traffic. And here, this is the definition. So a UDP flow is DTF if it has approximately the same average rate as a TCP flow in every short-time interval, such as a few round-trip times. And note that this definition implies that a DTF flow could have a different instantaneous rate than a TCP flow. So this is the definition of the DTF. Now, a large number of protocols have been developed based on this DTF definition. For example, TFRC stands for TCP-friendly rate control, and TCP emulation at receiver binomial. RIP stands for rate adaptation protocol, and SMD, the square increase multiplicative decrease protocol. But the problem of this DTF is that it has a very stringent requirement on UDP traffic. Okay, recall that DTF requires that a flow must have the same average rate as a TCP flow in every short-time interval. So this is a very stringent requirement. And because of this, this DTF considerably limits the design space of the TCP-friendly traffic control algorithms. Okay, so for example, those two types of algorithms are not DTF by definition. For example, the first one, any congestion control algorithm that maintains a long-term smooth standing rate is not DTF by definition. And also, any admission control algorithm is not DTF by definition. So then, our contributions. So we have two contributions. So first, we propose this stochastic TCP friendliness to greatly expand the design space of this TCP-friendly traffic control algorithms. And also this STF can still effectively prevent the internet from TCP starvation and congestion collapse. And second, we demonstrate that based on this STF, more efficient protocols can be developed for some applications. So now we have briefly introduced this TCP friendliness, and next I'll explain the definition of this stochastic TCP friendliness, and I'll also show you this TFCBR, which is an algorithm designed based on STF. And finally, the conclusions. So now first, what is this STF, the stochastic TCP friendliness? Now, our proposed STF measures the degree of TCP friendliness of a traffic control algorithm by its impact on the redistribution of all competing TCP flows. Let's consider a very simple example. And here we consider only a single bottleneck, and this link is shared by one UDP flow and 5 TCP flows. Those 5 TCP flows, they arrive at some random times and also send some random amount of data. Now, when this UDP flow is controlled by different algorithms, and we could have different redistribution of those 5 TCP flows. For example, and here when the UDP flow is controlled by some algorithm, let's say this is the redistribution of those 5 TCP flows. And when the UDP flow is controlled by another different algorithm, and here we may have a different redistribution of those 5 TCP flows. Okay? So now we can see that intuitively, the higher the impact of an algorithm on the TCP redistribution, the lower the degree of its TCP friendliness. So now let's consider this figure. In this figure, the x-axis is the impact of an algorithm on the TCP redistribution, so from less impact to more impact. And the y-axis is the degree of TCP friendliness, from less friendly to more friendly. So now if we have some algorithms, and then we should have a decreasing line like this, because the higher the impact, the lower the degree of TCP friendliness. So now if we have a threshold point, like the blue one in the figure, and then we can see that all the red points on the left-hand side of this blue point are STF with respect to this blue point. And all the algorithms on the right-hand side of this blue point are not STF with respect to this blue point. So this is the basic idea of our proposed STF. Now, to help you better understand this STF, now let's consider the difference between the traditional DTF and our proposed STF. Now, the traditional DTF considers the specific impact of UDP traffic on the rate of each individual TCP flow. And whereas our proposed STF considers the statistic impact of UDP traffic on the rate distribution of all TCP flows. Again, let's consider this simple example. So here we have one UDP flow and 5 TCP flows. So first, a reference case. In this case, even the UDP flow is also controlled by the TCP congestion control algorithm. So when the UDP is also controlled by this TCP congestion control algorithm, and then intuitively we should have the best TCP friendliness. So this is a reference case. So now let's say in this case, this is the rate distribution of those 5 TCP flows. Okay. Now in the second case, when the UDP flow is controlled by a DTF algorithm, because a DTF algorithm has little impact on the rate distribution of those 5 TCP flows. And then in this case, if you look at the rate of a TCP flow, for example, let's look at the TCP flow 2. We can see that the rate of TCP flow 2 is very similar to that in the first case. Okay, so the DTF has little impact on the rate of each individual TCP flow. This is the traditional DTF. Now in the third case, our proposed SDF. Now in the third case, if this UDP flow is controlled by a STF algorithm, now if we look at the rate of an individual TCP flow, for example, again the TCP flow 2, we can see that the rate of TCP flow 2 is quite different from that in the first case. Okay, so it does change the rate of each individual TCP flow. But if we now look at the rate distribution, we can see that in the third case, the rate distribution is very, very similar to that in the first case. So that is, this STF has little impact on the rate distribution of all TCP flows. So this is the difference between the DTF and STF.
You mean it's little impact on the sum rate?
Yes. So here we consider the distribution of all TCP flows, whereas the traditional DTF considers the rate of each individual TCP flow.
By distribution, though, you don't mean how they're actually distributed.
Okay.
It doesn't sound right to me. It sounds like what you really mean is the sum total of all the TCP
Okay, so this is just one example. If we, okay, so for example, if we know which TCP flow arrive at some specific time, but in general, again, look at this example here. We do not know the TCP flows arrive at some random time and also some random amount of data. So in general, we have a distribution for those 5 TCP flows.
When you redo these experiments, though, you're restarting you're deterministically running these random?
Okay, so for those 3 cases, those 5 TCP flows, they arrive at the same time for both 3 cases, and also a TCP flow sends the same amount of data for both cases, for all those 3 cases, and then we can compare those 3 cases fairly. Okay, but in general, that's a random variable.
Shouldn't, I mean, if you're adding one extra UDP flow, shouldn't the other rates go down?
Yeah, possibly.
Right.
Okay.
So even for let's say DTF, I mean, if you don't, I mean, if the TCP rates are the same, then the UDP has no.
Case 1 here has a UDP.
Oh, case 1 has the okay.
Yes. Okay. The point here is that the only difference between those 3 cases is that the UDP traffic is controlled by different algorithms. Okay, but we have the same amount of TCP traffic. Okay.
Just so I understand, is this simply a characterization about the aggregate of the flows, or is it also about the shape in the sense that whereas 2 over here is very low, if you notice 5 is now the same size as 2 had been before, 1 and 4 are the same size as 1 and 3, 4 is the same size as 3, and flow 5 is the same size as flow 2.
Okay. So how about
Is that an accident, or are you trying to bring out that it's more than the aggregate, it's also something about the shape?
Okay, so how about like this? Let's consider that we have a random variable. Okay, and for this random variable, in this case, we have 5 possible values. And also in the first case, we also have another random variable. We have another 5 possible values. So now let's say, what is the distribution in the first case and in the third case? You see. You can see that in both cases, we have the same distribution for this random variable.
Reordering of the random.
Yes, Okay.
Oh, so it's not just the aggregate.
It's not just the aggregate.
Okay.
Okay. Okay, so now it comes to the random variable. Okay. So now, in order to explain how to measure the impact, we start with 2 definitions. Let's say we're missing the first. Okay, just 1 second.
You can change the screen resolution to see more experiment.
Here. Oh, yeah. No, this is setting. This is already the lowest. That's okay.
Basically use a higher
1024
Slideshow. Oh, this is already.
No, I don't think you need that. I mean, low resolution. The projector actually should
Projector
have.
is probably 1024.
You see.
1024 you should use that.
Yeah,
Alright, yeah, I'm the resolution.
Okay. This one?
Okay.
Let's see.
Can you send me on that?
Oh, okay, great. Now it works. It's okay now. Okay, so we start with 2 random variables. So first random variable is xt. We use xt to denote the average rate of a TCP flow when the UDP traffic is controlled by the TCP congestion algorithm. So again, this is the reference case. Now, the second one, we use this random variable xpi to denote the average rate of a TCP flow when UDP traffic is controlled by a general traffic control algorithm pi. Okay, so now we have 2 random variables. Now, once we have those 2 random variables, and then we can measure the impact of this algorithm pi on the TCP root distribution by comparing x pi with xt in stochastic order. Okay, this stochastic ordering is a well-established topic in this probability theory for comparing two random variables, and this is a very good textbook on this topic. Okay, so now we are ready to give the formal definition of our proposed stochastic TCP friendliness. So we say that an algorithm pi is STF with respect to a TCP utility function set F if this inequality is true for any utility function F in set F. So this is the formal definition. Now, a TCP utility function is a function that maps the TCP rate to the user satisfaction. And intuitively, the higher the TCP rate, the higher the degree of user satisfaction. And therefore, intuitively, a TCP utility function is an increasing function. Or more accurately, we should say, it's a non-decreasing function. Okay? And then, according to the stochastic ordering theory, the larger the size of set F is, the less the impact of this algorithm pi on the TCP rate distribution is. In other words, the closer the random variable x pi is to this random variable xt. And then, therefore, the higher the degree of its TCP friendliness. So now we have a formal method to measure the impact of an algorithm on TCP rate distribution, and to formally measure the degree of its TCP friendliness. Now, intuitively, if we have an algorithm which is STF with respect to a TCP utility function set F, and then we know that this algorithm pi improves the overall satisfaction of all TCP users measured with any utility function in this set F. Okay. And finally, note that in this definition, we consider only the TCP utility function, which is a function of the TCP rate. But this definition can be easily extended to other types of TCP utility functions. For example, a function of the TCP response time. Okay. So now with this definition, we have defined 5 different degrees of TCP friendliness. So first, an extreme case. Now, this set F is empty. If F is empty, and then this algorithm has a huge impact on the TCP rate distribution, and we know that it's not TCP friendly. In another extreme case, if F contains all possible functions, in this case, according to the stochastic ordering theory, we know that in this case, an algorithm does not have any impact on TCP rate. So it does not change the rate distribution. It does not change the rate of each individual TCP flow. And therefore, we know that this case is actually the traditional DTF. And that is, the traditional DTF is a special case of our proposed STF. Now, between those two extreme cases, first let's consider if F contains all increasing functions. Now, in this case, according to this stochastic ordering theory, we know that an algorithm does not impair the cumulative distribution function of the TCP rate. And we call this case STF-ST, stands for STF in usual stochastic order. And next, if F contains only those increasing concave functions, and we call it STF-SCV, stands for STF in increasing concave order. And finally, if F contains all increasing linear functions, in this case, an algorithm does not reduce the average TCP rate, and we call it STF-mu, stands for STF in mean order. Okay, so now we have 5 different degrees of TCP friendliness. Now, let's look at the DTF again.
Quick question. 4 of those 5 have sort of human-friendly explanations. Is there an intuitive characteristic defined by F constraint contains all increasing concave functions?
Yeah, I'm going to discuss that next. Okay, thank you. So first, let's look at the DTF. So for the DTF, SF contains all functions. So if SF contains all functions, it also contains all increasing functions. So that means if an algorithm is DTF, it's also STF-ST. In other words, the group of all DTF algorithms is a subset of the group of all STF-ST algorithms. And also, similarly, we can show that the group of all STF-ST algorithms is a subset of the group of STF-SCV algorithms, which is in turn a subset of the group of all STF-mu algorithms. So now we can say that all traditional DTF algorithms are also STF-ST, STF-SCV, and also STF-mu. Okay. So then we have the next question here is, So we have those 5 different degrees of TCP friendliness. So which one is friendly enough? Okay. To answer this question, then we should consider another related question. So what are the utility functions of those TCP users in the internet? Let's start with the first one. The DTF, its F contains all functions. And therefore, this DTF is friendly enough to all TCP users because its F contains all functions. Okay. Now for the second one, for the STF, its F contains all increasing functions. So this STF-ST is friendly enough to all TCP users with an increasing utility function. But as we just discussed, any TCP user should have an increasing utility function. Okay, so no TCP user has a decreasing utility function, and therefore we know that this STF-ST is also friendly enough to all TCP users. So now we have a very important conclusion that this STF-ST is a sufficient and necessary condition for an algorithm to be friendly enough to all TCP users. Well, the traditional DTF is only a sufficient condition, but not the necessary condition. Okay, and next, this STF-SCV. Its F contains all increasing concave functions, so this STF-SCV is friendly enough to all TCP users with an increasing concave utility function. And usually we assume that all those traditional TCP users, for example, email users, web users, and FTP users, they have an increasing concave utility function. So this STF-SCV is friendly enough to all those traditional TCP users, but not to those multimedia streaming TCP users. Okay, and finally, this STF-mu, its F contains all increasing linear functions. In this case, an algorithm does not reduce the average TCP rate, so we know that this STF-mu is friendly enough to all TCP users who are interested in their average performance. Okay, so now we have those different degrees of TCP friendliness, and in our work, we are interested in the STF-ST because STF-ST is a sufficient and necessary condition for an algorithm to be friendly enough to all TCP users. And we are also interested in this STF-mu because this one is easy to analyze.
Just a quick question. I mean, what are the applications which is not using increasing concave functions? I think even all multimedia applications I can think of.
Okay. Usually in papers we assume that all those multimedia TCP users, their utility function looks like this. So not strictly concave. For example, sometimes we should have a minimum sending rate. If we below this point, and then the quality becomes, you say, unacceptable.
Okay.
Mm-hmm. Okay. I can show some papers talking about the utility function of different type of TCP users.
That would be interesting. Yeah.
Mm-hmm.
Is friendly enough, is that something you've defined? I mean, kind of by definition of what you're talking about here?
Okay, yes. So in this talk, we propose all those different types of STF definitions because traditionally we have only one definition, that is DTF. Okay, so because this DTF is a very stringent requirement, so you can see that it has a very limited small design space. Okay, so now we propose you see different type of STF.
I understand the nesting of this space here, but
yes.
when you use the words friendly enough, I'm wondering, I mean, is that something by definition or is that open to you?
Yeah, I see. That is just intuitively. Okay, because
all users have the same.
It didn't affect the rate flow of the
I mean, it's like experience, A experience of what B would experience, like B would experience.
okay. So when we say friendly enough, is according to our definition here.
Right? I mean, it's not like, if no DTF would be no change. The others, it's going to be some change for the rate.
I guess it's like if all users have the same thinking, right?
I think the friendliness, in a sense, is also a strong constraint. Basically, the friendless protocol by definition has less impact on the existing protocol, existing flows on the network. And I mean, many newer multimedia applications we are considering, for example, the telephone section. I thought you don't need to be friends. You only need basically to be fair. So you can, by definition, you actually want that traffic to grab a large share of the network. But
Yeah.
as long as you don't.
I'm just
Okay.
wondering, you're going to get some argument from somebody who's going to say, this is not friendly enough for me.
Okay. So when we say that it is friendly enough, that is, okay, actually that means it does not reduce the degree of the user satisfaction measured by some utility function. Okay, so if I'm friendly to you, that means I do not reduce your degree of satisfaction. That is friendly enough. Okay.
So
Mhm.
if F is your utility,
Yes,
and you
exactly.
replace T by pi, then you haven't.
Yeah, you should have at least the same degree of satisfaction. Mhm.
I think this is a very interesting, basically, framework.
Mhm.
I wonder if you basically explore other space of the framework. For example, currently, the utility function is related to the flow rate. Have you considered, for example, loss and delay?
No, not yet. But again, as I show here, so this definition can be extended to other types of utility functions. This is only the first
If you
step.
Extend it out. What's
Uh-huh.
the impact?
Mhm.
If delay and the loss rate actually can easily incorporate it as well.
Mhm.
In this.
Okay, I have a question.
Now I'm again unsatisfied because it's an expectation, this thing, right?
Yeah.
Oh, yes,
Okay,
yes.
So
Uh-huh.
meaning I may randomly swap with some other guy who's going through the same.
Yeah, exactly. That's the point. That's why here, in Tilt, it improves the overall satisfaction of all those TCP users. For an individual TCP user, your satisfaction may decrease. Yes.
When you say satisfaction here, do you mean simply the rate that I receive, the rate at which I can send?
It's the average rate.
But okay, so no, but if that's overall satisfaction, but my satisfaction as an
Mhm.
individual TCP user, that would be the rate that I'm able to send at.
Yeah. Yeah, for function of that.
A
Yes.
function of the rate.
Yes. An increase in
Why-
function of that.
Why a function of the rate? Why not a function of the proportion of the proportion that
yes.
successfully sent?
Okay.
Because if I'm sending it at a very high rate, I'm getting 20% through,
Mhm.
and we have some other people in the room, sending maybe at a lower rate, getting 80%,
Okay.
and then we
Mhm.
swap,
Mhm.
and they're getting all
Mhm.
of their bits through, and I'm getting now like 5%. That doesn't
Okay.
seem-
Okay, the short answer is that this one is easy to analyze, you see.
Okay.
Okay, and also this type of utility function is commonly used in the research papers. Okay. Mhm. Okay. So now we consider only those two types of TCP friendliness, the STF-ST and STF-MU. And then we use those two theorems to determine whether an algorithm is STF-ST or STF-MU. So first theorem, an algorithm is STF-ST if this inequality is true for any x. And intuitively, here, on the left-hand side, this is just the cumulative distribution function of random variable xt. And this one is just the cumulative distribution function of random variable x pi. So that means as long as the cumulative distribution function of pi is always no more than that of xt, and then this algorithm is STF-ST. Okay. For the second one, an algorithm pi is STF-MU as long as this inequality is true. And here again, this is the average TCP rate when the UDP is controlled by TCP algorithm. Again, a reference case. And the right side is the average TCP rate when the UDP is controlled by this algorithm pi. So that means as long as an algorithm does not reduce the average TCP rate, and then it's STF-MU. So we are going to use those two theorems to determine whether an algorithm is STF-ST or STF-MU. Okay, so this is the framework of our proposed STF. And next I'll show you an algorithm designed based on this STF. Okay, so this is the motivation of our proposed TCP-friendly and CBR-like rate control algorithm. Okay, motivations. Because some multimedia applications, they prefer a smooth sending rate for better user-perceived media quality. For example, a recent measurement study shows that the Skype users are very sensitive to the rate variation in an interval of 30 seconds. That means they prefer a smooth sending rate in an interval of 30 seconds. However, by definition, all those traditional DTF algorithms, they cannot maintain a smooth sending rate in such a long time interval. And therefore, we propose this TF-CBR with those two design goals. First, it can maintain a smooth sending rate in a time scale of 30 to 60 seconds. And also, this algorithm is STF-ST in most cases and is STF-mu in all cases. The reason that this algorithm is STF-ST only in most cases because it's almost impossible to design an algorithm which is STF-ST in all cases, where at the same time can maintain a smooth sending rate in a time scale of 30 to 60 seconds. Okay. Now, this is how we design this TF-CBR algorithm, which is quite simple with only 2 parameters. So first, the smoothness timescale alpha, which determines on what timescale this algorithm can maintain a smooth sending rate. The second parameter is the relative sending rate beta, which is defined as the average TCP rate divided by the average TCP rate. No, I'm sorry. Which is defined as the average TF-CBR rate divided by the average TCP rate on timescale of alpha seconds. So we use this alpha and beta to determine the sending rate of this TF-CBR protocol. Now, once we have the alpha and beta, this is how we implement this protocol. Now, we implement this TF-CBR by modifying the TFRC, because TFRC is not an internet standard, and also we know that TFRC can accurately measure the estimate the TCP rate in most cases. Now, this TFRC has 2 states, the slow start and congestion avoidance. In the slow start state, the TFRC just mimics the slow start of TCP, and in the congestion avoidance state, the TFRC adjusts its sending rate every round trip time, and it just sets its rate to the estimated TCP rate. Now, our proposed TF-CBR also has 2 states. In the slow start, the TF-CBR behaves exactly the same as TFRC. In the congestion avoidance state, our proposed TF-CBR adjusts its rate also every round trip time, but it sets its rate to this product. And here, this is this beta times the estimated average TCP rate in the past alpha second. And because of this, the TF-CBR can maintain a smooth sending rate in a time scale of alpha second, and also its relative sending rate is beta. Okay, so a very simple algorithm. But now the question is how to determine the value of alpha and beta. Okay, that's a hard question. Now, to determine the value of alpha and beta, and then we consider the parameter space. The x-axis is the smoothness timescale alpha from 0 to infinite, and the y-axis is the relative sending rate from 0 to infinite. And intuitively, we can see that as we increase the smoothness timescale and also as we increase this relative sending rate, this protocol becomes less TCP friendly. And that means this parameter space can be divided into 3 areas. So first, this STF-ST, and then STF-mu, and finally, not STF-mu. Okay. But the problem here is it's very hard to find the exact boundary line between those 3 areas, because the exact boundary lines, they depend on many network parameters. For example, number of TCP flows, number of UDP flows. So instead of determining the exact boundary lines, we consider only 3 special points in this parameter space. First, point A. Point A is the boundary point between the STF-mu and non-STF-mu areas when alpha is 0. And point B is the lowest boundary point between the STF-ST and STF-mu area when alpha is infinite. And finally, point C is the lowest boundary point between the STF-mu and non-STF-mu area when alpha is infinite. So we just analyze those 3 points. So first, for point A, intuitively we can see that when alpha is 0 and beta is 1, and then this TF-CBR behaves exactly the same as TCP, and therefore, if beta is no more than 1, it's both STF-ST and also STF-mu. And otherwise, it's neither STF-ST nor STF-mu. So now we know the location of this point A. But for point B, we have to use the theorem, okay, to determine the location point B. Now, in order to use the theorem, we should find out the cumulative distribution function of this xt and xpi. Okay. In order to get that, and now we propose 2 queuing models. Okay. So those 2 queuing models consider a single bottleneck link shared by a dynamic of TCP flows and a fixed number of long-lived UDP flows. The reason that here we consider those long-lived UDP flows because in this case, the smoothness timescale is infinite. That means this UDP flow maintains an infinite smoothness timescale, and that is this UDP flow has an infinite lifetime. That's why here we have those long-lived UDP flow. Okay. And also here, those 2 queuing models are flow-level queuing models. That is, we consider TCP flows and UDP flows, but not TCP packet or UDP packet. Now, The fixed queuing model is the model when the OTP flow is also controlled by the TCP congestion control algorithm. In this case, we have this MG1PS node. M means we model TCP flow arrivals with the person process, and G means we consider the general distribution of TCP flow sizes, and we have one processor sharing node. Okay, the reason that here we have some permanent customers is because all those UDP flows are long-lived UDP flows. So this is the queuing model for the first case. Now for the second case, when the UDP flow is controlled by this TFCBR algorithm, in this case, again, we have this MG1PS node. But because in this case, a TFCBR flow maintains a very smooth sending rate, that is, it consumes approximately the same amount of bandwidth. That's why here we have this reduced capacity. Now by analyzing those two queuing models, we can get this cumulative distribution function of the TCP rate, and then we can show that when alpha is infinite, only if this beta is 0, and then this algorithm is STF-ST for any network condition. So we have this point B at this location. And next, we analyze this point C. Okay, so we determine the location of point C by using this theorem. And in order to use this theorem, we have to find the average TCP rate in both cases. Again, we analyze those two queuing models, and we can show that when alpha is infinite, only if this beta is no more than 0.5, and then this algorithm is STF mu in all possible cases. Okay. And next, we have verified our flow level queuing model with packet level S2 simulation result. Those three figures are obtained with red routers. In the first figure, we have the TCP load is 10% of the bottleneck link capacity, and here 30% and 50%. Okay, so now by comparing those three figures with this analytical result, we have some observations. So first, this boundary line does depend on the network parameters. For example, here when we have different TCP load, we have different boundary lines. And second, the boundary line is a non-increasing function, and this is a very important observation. That means in order for an algorithm to maintain the same degree of TCP friendliness, as we increase the smoothness timescale, we should reduce its average sending rate. Okay, and next, we can see that among all those simulation results, the lowest boundary point between the STF mu and non-STF mu is this 408, and which is consistent with our analytical result. And also the lowest boundary point between STF-ST and STF mu is here, it's 108. It's already very close to our analytical result 0. Okay, so this is the simulation result obtained with red routers. We also have simulation result obtained with drop tail routers. So slightly different, but we can see the same pattern here. Okay, so now based on the simulation result and analytical result, finally we choose this red point as the parameter of this TFCBR. At this red point, the alpha is 60 seconds, and that means we can maintain a smooth sending rate in an interval of 60 seconds. And the beta is 0.5, and from here we can see that when beta is 0.5, it is STF-ST in most cases. And also because beta is 0.5, so it's no more than this point C, it is STF mu in all possible cases. So, and then this TFCBR can achieve our two design goals. Okay, next I'll show some simulation result. So we have simulated 3 types of TCP flows, and we have simulated 3 types of UDP traffic control algorithms. And here I'll show you only the result for the short-lived TCP flows arriving at the person process, and the result with TFRC, and the result with TFCBR. So first we study whether this TFCBR can maintain a smooth sending rate in an interval of 60 seconds. Now, the left figure shows this coefficient of variation of TFRC and TFCBR in an interval of 60 seconds. Intuitively, the lower the COV, the smoother this protocol. And from here we can see that the green one is the coefficient of variation of TFCBR. And the red one is the COV of this TFRC. We can see that the green one is much lower than this red one. That means our proposed TFCBR is much smoother than TFRC. And to help you understand the smoothness difference, and the red figure shows the 1 second average sending rate of TFRC and TFCBR when the TCP load is 30% of the bottleneck link capacity. From here we can see that the green one this is the sending rate of TFCBR. The red one is the sending rate of TFRC. We can see that the TFCBR is much smoother than TFRC. It's almost a constant bit rate in an interval of 60 seconds. So this is our first design goal. And then next, we study whether our algorithm is STF-ST in most cases. Now, we use this theorem to determine whether our algorithm is STF-ST. Now, in each figure, the green line is the cumulative distribution function when, it's the cumulative distribution function of TCP rate when the UDP is controlled by this TFCBR. And the red one is the cumulative distribution function of TCP rate when the UDP is controlled by TFRC. Now, according to the theorem, as long as this green line is always no more than the red one, and then it is STF-ST. So from here we can see that in 3 figures it is STF-ST. Only in the first figure it's not STF-ST. So that is STF-ST in most cases. And finally, whether it's STF-mu in all cases. So we use this theorem to determine whether it's STF-mu. And here, the green one is average TCP rate when competing with TFRC. The red one is average TCP rate when competing with, red one is the average TCP rate when competing with TFRC. Green one is for the TFCBR. And according to the theorem, as long as this green line is always above this red one, and then it is STF-mu. So here we can see that it is STF-mu in all cases.
I'm sorry, I didn't catch what your definition of TCP load there is.
Okay.
Is that the desired amount that TCP is trying to use of the total link bandwidth? Is it the percentage of the actual
Okay.
use of the link?
So here, this is how we define the TCP load. If there is no UDP traffic, and we measure the amount of the TCP traffic, and then in the first case, amount of TCP traffic is 10% of the bottleneck link capacity. Okay, and in third case, it's 30% of the bottleneck link capacity.
Okay, so does the offered UDP load then bring it up to try to use the entire link capacity, or are you just not stressing the link capacity?
We still have the link capacity is fixed. Okay.
Yes, but are you trying to exceed the link capacity with your total cumulative flows here, or are you not?
What do you mean by exceed the link capacity?
I mean, are the senders, if the link capacity, are they trying to use the entire link capacity, or are they perfectly happy sending at their maximum rates within the link capacity?
Okay.
In other words, are the routers ever dropping any packets?
Okay. So even in the first case, when we have only 10% of the link capacity, we still have the packet losses, because in this case, the TCP flows arrive as a person process. So sometimes we still have packet losses. Okay. So this is how we design our simulation. So first, there's no UDP traffic, and then we have only those TCP flows arrive as a person process. So we just control this parameter lambda so that, the average TCP traffic is 10% of the link capacity, and then we add those UDP flows. We still have the same lambda for those TCP traffic.
What do you mean the TCP traffic is a plus-on process?
Okay. The TCP flow, we control the inter-arrival time between TCP flow arrivals. Okay.
Between the flow arrivals?
Yes. Okay. No. Flow arrivals. So remember that here, this model is the flow level model. Okay. If we consider the packet arrivals.
So they have a lifetime too, right?
Yes, exactly.
What is the lifetime?
For the lifetime, we use a very general distribution. It's not the exponential distribution. Okay.
But your example here only shows short-lived TCP flows.
We also have, you say, long-lived TCP flows. We also have the short-lived TCP flows generated by using this packet-man. Also, we have simulations with a mix of them.
So I'm curious, you said you were only showing the short-lived TCP flows. So
in those figures.
The long-lived ones look worse, or?
No, not worse. Yes. Okay.
So why were you picking those to show the long-lived?
Actually, it doesn't matter because it's just the first one here. Actually, we have all the simulation results in our paper. You can see that we can still make the same conclusions based on the simulation result.
Let me repeat the experiment conditions.
Okay.
So basically, you generate short-lived TCP flow with a certain lifetime of the flow, and they are arriving according to a process
Mhm.
at a short lived and long lived, and you control the total load.
Yes.
Meaning 10%, 30%.
Yeah, exactly.
And your traffic is actually, trying to occupy the pipe. And you are basically seeing if your traffic is injected, if it's injected, let's say using a normal, basically TCP control protocol, or using this designed TFCBR or TFRC protocol,
Mhm.
how the rest of the TCP flows flow distribution changes, right? So basically,
Yes. The impact of the UDP traffic control algorithm on the rate distribution of those competing TCP flows. So this is why we say this is just the TCP friendliness problem. We consider the impact of UDP on the rate distribution of TCP flows. Okay.
Let me ask this question. Go to the slide where you have this one.
Okay.
I notice your beta parameter is basically half.
60 seconds.
No, sorry.
Oh, beta is 0.5. Yes.
Beta is 0.5.
Yes.
And the TCP AIMD,
Mhm.
basically the drop is also half.
Mhm.
So intuitively, you control your rate to be about half of the calculated basic TCP.
Half of the TFRC.
Right?
Mhm.
So I noticed basically the ring curve almost stay at the bottom
Ah.
of the red curve.
Yeah. So this is the 1 second average rate. Okay. The round trip time is much less than this 1 second. So if we measure this, the 1 RTT average rate, and then you will see something as you expected. Okay. So for example, if it's only 1 RTT average rate, and then this point should be much lower.
Okay. My only comment is that this seems put yourself at a big account. This protocol.
Exactly. So that's the point. Okay, so that's why remember we have a very important conclusion. In order to maintain the same degree of TCP friendliness, when you increase the smoothness time scale, you should reduce your average sending rate.
So this is
Okay.
a penalty.
Yeah, exactly. That's the point.
When we want to-
If you do not care about this TCP friendliness, and then you can have any smoothness time scale, and you have any sending rate. Okay, but as long as you consider this TCP friendliness, there is a trade-off between the average sending rate and the smoothness time scale. Okay. Just one more slide here. Also, we studied the fairness and convergence speed when we have multiple TF CBR flows. Okay, so in this figure, we have one TF CBR flow start at 100 seconds, the next one 200 seconds, the third one 300 seconds. We can see that they can still fairly converge to this fair bandwidth share, while at the same time maintain a relative smooth sending rate. This is the result for TFRC. Okay, again, we can see that even though it can quickly converge to the fair bandwidth share, but its sending rate is not smooth at all.
For this, what is the basically bottleneck capacity? Why? When it's one flow or two flows, why the flow rate is not 3 times the flow rate when you have 3 flows flow out there? So for them during 300 to 600 seconds, I would say the average sending rate is about 2 megabits per second.
Yes.
During 100 and 200 seconds, you only have one red flow. Why doesn't you use something like 6 megabits per second?
Okay, so that's a very good question, but I do not have the answer for that. I forgot the details of the simulation. Yeah. Okay, so I can find that for you after this talk.
Were there any other flows when this was done?
In this case, we do not have those TCP traffic. We have only those 3 UDP flows.
Was the traffic being injected?
Mm-hmm.
How was the traffic being injected? Was it constant rate? Was it pulse
Okay. For example, in this figure, we have only 3 UDP flows. One start at this point, another one here, another one here.
Yeah, but the flow is sending data.
Yeah,
Is it sending data constant at a uniform rate, or is it sending data in a choppy way? Is it sending it?
Okay. So the source always has the data available. So its sending rate depends on.
Okay, I see.
Yes.
So it just has like a lot of, it has more than it can afford to send.
Yes.
It's just sending at the maximum rate it's allowed.
Yeah, exactly.
Got it.
Okay, so finally the conclusion. So now we propose this STF to considerably expand the design space of this TCP-friendly traffic control algorithms, and also we propose this TFCBR to demonstrate that sometimes we can develop more efficient protocols based on this STF. And we believe that our work on this STF is an important step to safely relax the definition of the current TCP friendliness, and also help the internet to move from a world dominated by TCP users to a world friendly shared by those diverse users. Okay.
I think we may want to even stretch the boundary even more. Because, I mean, think about different applications. They have different utilities.
Yes.
File download have a utility which actually, I mean, is much more tolerant to rate drop versus, I mean, if I'm starting a video conferencing session or video streaming session, ideally I want to have more rate.
Okay. Actually, we have another recent paper where we extend this definition of STF-MU. So here, in this case, if an algorithm is STF-MU and then it does not change the average TCP rate. And we have another definition. It's called, for example, X STF-MU. In that case, your average TCP rate is only X% of this average TCP rate. For example, it's only 10% of the average TCP rate. In this case, you can have a higher sending rate and also will maintain a longer smoothness time scale. But again, that's a trade-off. Okay.
Interesting question. Interesting problem.
And also from here, we can see that why this fairness, the fairness problem is more harder than this friendliness problem, because there we have to define what is the fairness. But usually, it's very hard to define what is the fair between the TCP and the UDP.
So is it good if we define fairness as basically as maximizing the total utility
Okay.
of all applications in the network, with utility defined in some measure? So for example,
Yeah, that is one definition. Yes.
so instead of basically trying to maintain fairness, meaning basically I'm trying to make sure ST is smaller than SI, right? I'm basically saying, okay, let's add everything together. And as a network, I want to maximize the total utility of all the functions.
Yes. Okay. So any more questions about this? Okay. So this is the first part. Okay, this is the first part of our talk. It's about TCP friendliness. Okay.
See about the peer-to-peer part.
Okay.
Thank you. Professor Lee.
Oh yeah. Thank you. Okay. Go ahead.
Do you want to get the microphone?
Oh yes.
We have several copies of the paper discussing the simulation results.
Yeah, thank you.
I'm Miao Wang, a fourth-year graduate student at the University. I'm a fourth-year graduate student at the University of Nebraska. I'm very glad to stand here to give a talk discussing my recent research, because I have read lots of papers from Microsoft discussing of network coding in CDN networks and ISP-friendly rate control in the P2P streaming. Now, my research focuses on the multi-view peer-to-peer systems that which we'll discuss later. First, I will introduce what is a multi-view system, and now I will define the bandwidth allocation problem in the multi-view systems. And then I will show you three general designs for building such systems by solving the bandwidth allocation problem. And then I will conclude the paper with the future work. First, the introduction to multi-view systems. The peer-to-peer systems have been successfully supports hundreds of channels with millions of users. And here are some successful applications in China and in the US. most of the commercial applications allow the user to watch one channel at a time. So usually the servers and peers in the network are organized into overlays, which are the logical relationship among users and the servers. And then the servers and the user can contribute their bandwidth to the system to sustain a specific stream rate for a specific channel. Therefore, the single view system appear in this system can watch only one channel at a time. Therefore, there's no overlap between the overlays. For example, the overlay 1 for channel A and the overlay for channel B, that do not overlap each other. And the peer can only contribute its bandwidth to only one channel. While in multi-view systems, a peer might be able to watch multiple channels at the same time. For example, here, the user U1, U2, and U3 watch both channel A and channel B. Therefore, their overlay overlaps with each other. And the peer can contribute its upload bandwidth to both channels. Before going through the bandwidth allocation problem, I first introduced some applications of the multi-view systems. In general, there are two categories of applications. First, it's called the multi-view internet TV applications. For example, a user might watch a high-definition video on the large screen and then monitor the weather information on small screen. Another kind of application is called the multi-camera live streaming application. That is, you can watch a car racing from different views of the cameras. Now I will describe what is the bandwidth allocation problem in designing the multi-view systems. Based on some recent measurement study, in the current P2P systems, the bandwidth is imbalanced among different channels. For example, in the two-channel case, channel A may not have sufficient bandwidth to sustain a stream rate of that channel, and the channel B might have bandwidth surplus in that channel. And the peers watching both channels have to decide how to allocate its bandwidth. That is, if they acquire this bandwidth imbalance, these users will allocate more bandwidth to the channel with bandwidth deficient. Therefore, we define this allocation problem like this. The demand of a channel is that each overlay needs to bandwidth sustain the stream rate R for all participating peers in that channel. For example, channel 1 then need bandwidth to sustain peers U1, U2, U3, and U4 and U5, and similar for channel 2. They have to require bandwidth to supply to sustain U1, U2, U3, and U6 and U7. And the supply of the system is the bandwidth at peers and the servers. There is a competition between different overlays. For example, user U5 and U7 will compete upload bandwidth at peers U3. And the problem is that the peers joining multiple channels have to determine how to allocate the bandwidth based on each channel's bandwidth supply and demand. So that should acquire the bandwidth imbalance of different channels. We use this resource allocation graph to define this problem clearly. First, in the first row of the vertices, we call it the bandwidth suppliers. For example, the SA means the total upload bandwidth of peers watching only channel A. That is the peers U4 and U5. And S sub AB means that the total upload bandwidth of peers watching both channels, including the server bandwidth, because currently you can see the server can contribute its bandwidth to both channels. That is the bandwidth of U1, U2, U3 plus the server bandwidth S1, S2, and the S sub B is the bandwidth demand, upload bandwidth of peers watching only channel B. That is peers U6 and U7. Then what is below is we call it consumers. that is they request the bandwidth from the suppliers to sustain their stream rate. The demand, the A denotes the bandwidth demand of peers watching channel A. It includes 5 peers, that is U1 to U5, and B represents the bandwidth demand of peers watching channel B, that is the peers U1 to 3 plus U6 and U7. Then, based on this graph, that is the consumer A can only request the bandwidth from supplier S sub A and the supplier S sub AB, and B can only request bandwidth from supplier sub SAB and the supplier sub S sub B. So it's a basic choice of designing the system. Now I will introduce the 3 general designs of building the system by solving this problem. In particular, we are trying to answer the 2 questions. First, what are the general characteristics of these designs? And the second question is, under what circumstances should a particular design be used to achieve the desired streaming quality with lowest implementation complexity? This is an overview of the 3 designs. All the 3 designs focus on solving the bandwidth allocation problem introduced before. For the first is a naive bandwidth allocation, that just simply allocated bandwidth. I will introduce it later. And the passive channel aware design, there are 2 examples. The first is the all-at-once approach proposed in Infocom 2007 by Professor Baochun Li from University of Toronto. And another example is our design protocol called the divide and conquer protocol. One example of the active channel aware design is the view and upload decoupling approach proposed by some professors from the Polytech University in New York. First, I will introduce the naive bandwidth allocation approach. That is, a user can only join its watched channels, and then it allocates its upload bandwidth to its watched channels proportional to the channel streaming rate. For example, the U1, U2, and U3 should allocate its upload bandwidth to channel A and channel B based on the streaming rate of channel A and channel B. If we assume that both channels have the same stream rate, then they will allocate half its bandwidth to channel A and half its bandwidth to channel B. The passive channel bandwidth allocation, in this approach, also the peers can only join its watched channels, and then these peers will aware the bandwidth imbalance of different channels, and then they allocate more bandwidth to channel A. The third approach is called active channel bandwidth allocation. That is, a peer might not only join its watched channel, and it can also join its unwatched channels as a helper, and then they allocate its bandwidth by being aware the bandwidth imbalance. For example, the users U7 watching channel B can join the channel A, its unwatched channels, to help user 5. We draw this figure to show the efficiency and the complexity of the 3 designs. The x-axis is the implementation complexity from less complex to more complex, and the y-axis means the efficiency of bandwidth utilization. First, the NBA design, it does not require any actual information, and so the implementation complexity is the lowest. But it does not aware the bandwidth imbalance among different channels. So the bandwidth utilization efficiency is the lowest. And the active channel aware design is ACA design. It requires the most information of the system, that is the bandwidth imbalance and which peer should join which channel. So the implementation complexity is the most complex, and but it's most efficient to use the the bandwidth in a system, and the PCA design is fall in between. Now our research is to compare the relative order of the three designs and to show under what circumstances which design should be used. Comparing the three designs, we want to use some optimization method to compare the three designs. First, each channel wants to maximize its total obtained bandwidth. Therefore, we define the bandwidth satisfaction ratio of channel A is that the total obtained bandwidth over the total required bandwidth, and the optimization model should be like this. Oh, okay.
Are you assuming here that the basically the last mile is the restrictive point here? Because what does upload bandwidth mean otherwise?
Yes. We assume that we only consider the end-to-end bandwidth, that is the last mile bandwidth. It's not the bandwidth in the backbone. I mean it's peers access bandwidth to the network. Like if they use a DSL, they have access bandwidth.
So you're generally assuming the backbone has infinite bandwidth here? Is that sort of
That's the assumption in this paper.
Yes.
And also this is from some recent measurement of P2P papers. It shows that in most cases the last mile is the bottleneck.
Then the optimization model like this. The objective is to maximizing the aggregated bandwidth satisfaction ratio of all channels, and the constraint is that the total amount of bandwidth allocated at each peer cannot exceed its physical capacity. Here we use a network flow to show what the problem is. Here in the middle part, that is the resource allocation graph we just introduced before. And the capacity here for the NBA design, it is fixed. Because, for example, here, the supplier S sub A allocates all its bandwidth UA to A, and the supplier S sub B allocates half its bandwidth to A and half its bandwidth to B, because we assume that both channels have the same streaming rate. And then we add several virtual vertices. The first one is the source vertices, and the other one is the sink vertices. The capacity between the source and the consumer is the demand of the consumer, and our goal is to sending maximum flows through this network to saturate these two edges. If these two edges are saturated, we see that this then can satisfy all the bandwidth requirement by all consumers. Otherwise, we see that this then cannot achieve the optimization goal. Here it is the optimization model of the PCA design. Here the difference is that we do not know how much bandwidth it will allocate. The supplier S sub AB will allocate to consumer A, and how much bandwidth it will allocate to consumer B. We just use this flow network to determine whether they can saturate these two edges. For the ACA design, because the peer can join its onboard channels, so it is possible that the consumer A can request the bandwidth from the supplier S sub B, and also the consumer B can request the bandwidth from the supplier S sub A. And then we also want to know whether this design can saturate these two edges. There are two groups of parameters will influence the three designs. First, we call it the channel information parameter. That is the streaming rate of each channel. It can be homogeneous. That is, each channel has the same streaming rate, and it can be heterogeneous. That is, each channel have different streaming rates. Another is the channel structure. It is whether two or more channels overlap with each other. A second group of information of parameters is the system information parameters. That is the number of channels and number of peers. A second is the bandwidth distribution of channel sites and the population distribution of channel sites. Typically, we study three channel structures. The first one is called the chain structure. That it corresponds to peers watching a consecutive row of cameras. And the second one is called the mass structure. That is, peers can randomly, can arbitrarily watch some channels. And the third one is called the star structure. That is, there's one popular channel that everyone watches, and then everyone can watch another their preferred channel. In order to study, to compare the relative order of three designs, we use some simulations. First, we want to control the population distributions. We use a beta distribution to control to generate a distribution, and then we arrange channel sets in lexicographical order. That is, for example, if the system has 3 channels, we arrange them in this order, and we generate this distribution with the beta distribution, and then assign a fraction to each channel set, a fraction f, and then we can determine how many peers in this channel set. Similarly, we control the bandwidth distribution in this way, but we want to compare the relative order of 3 designs. Therefore, we control the total upload bandwidth is sufficient to support all peers. That is, to guarantee the ACA design can always achieve the optimal bandwidth allocation. And we can see that the design space is determined by the bandwidth distribution and the population distribution, and it is continuous. And we want to divide the continuous design space into the discrete space by the 7 distribution. For example, if we use this distribution to control the population, it means that most peers watch some popular channel, and if we use this distribution to control the population, it means that most peers watch multiple channels. And if we use this distribution to control the bandwidth, it means that peers watching some channels, they have more bandwidth than others. Therefore, the design space is divided into 7 by 7 discrete spaces. Before showing the result of the whole space, I studied the 2-channel homogeneous system like this. In the system, we have 2 channels, channel A and B, and a fraction of peers watching both channels. And the streaming rate and upload bandwidth of the peers are the same. Here is the x-axis is the fraction of peers watching channel B, and the fraction of the y-axis is the fraction of peers watching channel A. Then the whole space is just a lower triangle, because the above triangle is that upper triangle is that is invalid because the sum of the 2 fractions exceeds 1. And when the ratio of the streaming rate over the upload bandwidth is less than 0.5, less than or equal to 0.5, is that all 3 designs can satisfy can achieve the optimal bandwidth allocation. Therefore, we can use the simplest design, the NBA design. If we increase the ratio,
I don't understand why. You can't have 100% of them watching both channels?
You can have 100%.
That's the left bottom point.
Yes, here.
Okay, so you have both zeros.
Yes, you have the fraction of peers watching channel A and watching channel B are 0, and all of them watching both channels A and B. Because the 3 fractions, the sum of the 3 fractions.
This is a population watching only channels.
Oh yes, yes. And when we increase the ratio of streaming rate over the upload bandwidth, we can see that the solution space of the 3 designs shrinks. And in this special case, the PCA design and the ACA design has the same solution space, and therefore we just draw the PCA design, ACA design, and the NBA design. We can say in this area we should use the PCA design, and in this area we should use the NBA design. And now I will show you the general system, the general simulation results that we simulate, and the space is divided by the 7x7 distributions. First we simulate the homogeneous the system with homogeneous streaming rate, and we can see that the solution space of PCA design increases when it changes from chain to mesh, and also we change the streaming rate from low, like 300 kilobytes, to high, that is 1 megabps, and this does not change the size of the space.
Sorry, I'm getting lost.
Okay.
Go back to the previous slide.
Okay.
So I thought these. So what are the purple regions and the?
Okay, so here the point is, if the color is purple, that means at this point you can use any of those 3 designs. You can still achieve optimal performance. So if the color is purple, that means in this case it's better to just use NBA because it's the easiest one to implement. You can still achieve the best performance. But if the color is the red one, in that case, then you can use either the PCA or ACA. Okay, because if the color is red, and then only the PCA or ACA can achieve the best performance. The NBA cannot achieve performance. But if the color is red, in this case, because the PCA is easier to implement than ACA, and then it's better to just use PCA, because in this case, PCA can achieve the best performance with the lowest implementation complexity. Okay? Because fundamentally here we consider this question: which design method can achieve the best performance with the lowest implementation complexity?
So in that white area, I guess you just want the.
Okay, if the color is red, that means none of them can achieve the best performance because now the resource is insufficient. In this case, and then it's necessary to use the admission control. Right? So for example, in this case, this peer cannot watch 2 channels. If you watch 2 channels, and then we do not have enough bandwidth to support that.
Okay, so what's R over U?
R over U is the streaming rate over the bandwidth. That's a ratio that how close your streaming rate is close to your upload bandwidth. The close means that the larger of the value means there's maybe there is less bandwidth in the system to sustain all the peers to watch both channels.
In other words, this U is the average upload capacity of a user. R is the streaming rate.
Yeah, because we studied the homogeneous system that is the system we can get a closed form solution to describe the size of the space here. So this is a special case.
Okay, so if it's a half, wherever U is a half, then you can support 2 streams fully.
For all the peers, yeah.
For all the peers.
Yes, that's why here, if R over U is less than or equal to 0.5, we have all the 3 designs can achieve the optimal. Yeah.
Okay.
Sorry, I just confused you.
And then okay. So that's why the white regions are unachievable.
Yes.
Okay.
Here, this is the invalid region actually. And then we can see that the infeasible region increases as the value R over U increases. Now we study more general cases that with.
Sorry, tell me intuitively why the shapes look like this?
Oh.
So intuitively, if you look at the left bottom point, and there we have more and more users watching both channels. If we have more and more users watching both channels, and then we require more bandwidth. Okay, that's why at that point, the resource is insufficient, and not then achieve the best performance. Yeah, that's why I said in that case we should have this animation control.
Right. Okay. But I mean the colors. Why are the colors shaped like that?
The color shape is we can see that it's in this special case it's a symmetric system. So the figure should be symmetric along this line,
Okay.
and then here it is. It means that if we only simply allocate half bandwidth to channel A and half bandwidth to channel B, we cannot achieve the optimal bandwidth allocation. We should aware the bandwidth difference. So it's different. It's like
Okay.
this here. Okay.
So the next slide.
No. Okay. Now currently we are starting the more general cases with the general bandwidth distribution and the general population distribution. In idle case, it should be continuous. We should show you a figure.
What are the axes here? What are we looking at?
Okay, we use these 7 distributions to control both the bandwidth and the population distribution, and then it should be a 7 by 7 squares.
Okay.
So we just divide the continuous data space into discrete space.
Okay.
And then we use simulation to test the model, that is whether we can saturate the edges on the flow network to see. We can see the blue. Okay, there's no better way. The blue means that there is a feasible solution for the design, and the gray means that there is no solution. And then we can see that when the PCA design can achieve the best performance with the mesh channel structure. That is a general case in the multi-view systems. But for the special case, for example, the chain structure, that is a peer watching a row of cameras, they cannot achieve good performance. We need the advanced design. And then we also increase the streaming rate from low to high. That is, we want to compare whether the streaming rate is as an influential factor of the design. We found that it does not change the size of space. Also, we simulate a heterogeneous streaming system. That is, we can in our simulation we have 30% of channels has low streaming quality. 30% of channels have medium streaming quality, and the other 40% have high streaming quality. We can see that the PCA design can never achieve the optimal solution with the chain and star structure, but for the mesh, it can still achieve the best solution. Therefore, our conclusion is that current conclusion is that the NBA design can really achieve the desired streaming quality in general cases. And for the mesh channel structure, the PCA design can achieve the same performance as AC design. Therefore, we have to use a simpler PCA design to design a multi-view system. For special channel structures, for example, the chain and the star, we should use AC design to improve the quality. And the future work, that is my current work, is that I want to use the sensitivity analysis to find out the key factors that will influence the size of the space. And the second is find out the performance threshold. I believe that there exists some thresholds in the system. For example, the average number of views that is in the system, that is how many views the peer should watch, that will influence the size of the space. And then the third one is applying the results into the single view systems. For example, here.
You know, we're really over this thing.
Okay.
This is the
Last one. This last one.
Just want to be
Yeah, that's
Okay. It's a.
Okay.
Okay, let's close.
So, let's close the talk. Thank you very much.
Okay, thank
you.